Hello, and welcome to another IoT Central webinar. I'm David O'Hara, and I'm the Managing Director at IoT Central. I'd like to start by thanking our sponsor, Ground Control. Ground Control is a leading supporter of the IoT Central community, and we're grateful to have them as sponsors. Today's webinar is titled IP versus Messaging for Satellite IoT Data Transmission. Our speakers are Alistair McLeod, CEO of Ground Control, and Rick Searle, Group CTO at Ground Control. Gentlemen, when you're ready, let's get started.
All right, well, thank you, David. It's great to be back at IoT Central. For those who didn't catch us last time, this is the second of our series of 6 webinars on various topics related to using satellite for IoT. If you didn't catch it, the last one was focusing on 3GPP and whether that's going to accelerate standards. But let's do some intros first. I'll start with myself. I'm Alistair, I'm the CEO of Ground Control, long-time guy in sort of tech and telco, but relatively new to satellite. I've been here for about 3.5 years. When I'm not doing tech stuff for Ground Control, I'm either flying an airplane or sailing a boat, at least when I get half a chance. Rick?
So I'm Rick Searle. My career started as a electronics engineer by training, but I actually took a career as a professional sailor for quite a few years. When I realized I needed a real job, I sort of self-taught myself how to write code and founded YB Tracking, which was a business that created tracking solutions for sailboats so that when races happened and boats went over the horizon, people could still know where they were. That sort of evolved into Rock7, which became an IoT business. Our sort of biggest selling product was a product called RockBlock, which was enabled makers using things like Arduino to send and receive short messages using the Iridium platform. And that business was eventually sold to Ground Control. And I'm now the group CTO here.
All right, so let's kick off with these are the topics we're going to cover today. And obviously the headline, we're looking at TCP/IP comms for satellite IoT and comparing and contrasting that to messaging. So this is the flow of the webinar for today. I'm going to do some quick what's the difference thing, just to sort of set the scene. Then Rick's going to get straight into TCP/IP, more detailed design considerations, optimizations, and so on. We'll pivot in the middle to messaging for IoT over satellite, and then again Rick will dive into the detail, and I will wrap things up at the end and hang it back to David. Let's start with just the high level. Why are we even talking about this, and what's the point? I'm sure all these terms are very familiar to you, but just by way of an intro, TCP/IP, ubiquitous, interactive two-way communications, undoubtedly the most widely used communication protocol, used kind of literally everywhere. If that's in the context of IoT, what would that look like? On the Iridium network, it would look like a Certus connection. On the Inmarsat Viasat network, it would look like a BGAN connection, but you might also have come across it in more traditional satellite services like Viasat MSS, or probably most likely you come across it in the context of 4G, LTE, cellular IoT, but all basically hanging off a TCP/IP connection. So messaging, what's the difference? Well, messaging, the analog I always use for people is messaging in IoT is kind of it's the SMS equivalent of a phone call. Literally, it's the SMS equivalent. So we're sending packets of information. With messaging, we only send what's required. The advantage of messaging, because it's a store and forward technology, is you only need to send it when it's needed. You don't have to stream it. So you can be super efficient with how much you send over the satellite, which can be a consideration for use cases. And you'll come across it in satellite IoT. Iridium has a service called Short Burst Data. Inmarsat has a service called Inmarsat Data Pro, ISAT Data Pro. Of course, SMS still turns up. The thing which we'll get into later that you just need to keep in mind with messaging is almost invariably it involves more effort and more engineering, although you may well come out with a more efficient solution at the end. So that's your basic compare and contrast. Now I'll hand over to Rick, who's going to jump straight into TCP/IP in more detail.
Thank you. I'm going to take the liberty of assuming there are very few remote IoT solutions that are pure satellite or that thought about satellite from the very beginning. It's much more usual that something was built using the most common networking technology there is, which is TCP/IP. So when we're considering deploying it further afield by adopting satellite, the most obvious benefit of using TCP/IP is that you don't need to change any part of your remote system. It'll probably just work, it'll be plug and play. TCP is really reliable, it's well understood, and if you need a low latency, real-time conversation between your remote things and your servers, then it's very, very well suited. The satellite operators know this, and they've built really, really good IP services on their networks to pave the way for smooth adoption. It's the fastest way for them to get new subscribers onto their network. But the networks don't actually love it, especially for IoT data. For small payloads, using TCP/IP is incredibly inefficient, and it wastes resources on the satellite. Flying satellite constellations is an expensive business, so the networks charge high prices for capacity, and they charge those prices whether it's used efficiently or not. So with small data volumes like sensor readings, which are very typical in IoT applications, using TCP/IP can be orders of magnitude less efficient than some of the alternative transports that the networks would prefer you to use. I think it would be good to think about what we really mean by IP-based comms. Actually, IP is just the network layer protocol in a whole stack of layers that most internet applications rely on. IP is just a protocol that gets data packets moved from one place to another in a packet switched network. And maybe the first alarm bell should be that most IoT satellite applications look much more like a point-to-point link. So you've got remote systems all talking to a single cloud service. So we don't really need all of the addressing and routing capability of IP. And IP on its own isn't really good enough. It doesn't care if things go missing. So we typically have to always add another layer to add some reliability. And usually this is TCP, Transmission Control Protocol. This makes sure that the sender and the receiver can both know that the data arrived intact. It takes care of packets that go missing, it resends them if necessary. If packets are reordered, it can sort that out too. But to do this, it requires quite a lot of conversation between client and server. And this chat doesn't contain any useful information to you, but the satellite has to carry it and you have to pay for it. Even TCP probably isn't enough for your application on its own, and so we tend to invent session or application layer protocols to help a client and server agree how to talk to each other. In many IoT applications, this could be HTTP. This protocol was originally intended for serving up web pages to browsers, but it's become lazily adopted as a sort of good enough request response protocol for client and server comms. But even HTTP, it's just moving documents around. Our client and our server both need to agree on what goes into the document, so there's probably an agreed language between them. In IoT, this is often a JSON document, and it's very rarely optimized to be data efficient. We often see human readable text in these protocols that bloat the data maybe 10 or 100 times. And every one of these layers adds metadata or control data, which is what we're trying to show in this diagram on the left. When you're throwing big files around the internet, this doesn't matter. The overhead is probably less than 1%. But a lot of IoT applications that only have tiny data or tiny amounts of interesting information, and that's the blue part in these diagrams, if you only have a few bytes of information to exchange, you could easily see a few thousand bytes actually transmitted. And when you're paying for every byte, or when you're using a slow link and you care about the latency or the capacity of that link, that really matters. What you can do about this all depends on how much control you have over your remote application. In this section, I'm assuming that completely rewriting it isn't an option. And probably the same application still needs to work with a cellular network. And so we're not going to throw away our TCP/IP and application layers. It's obvious, but the more you can do to reduce the volume of data you're sending, the more efficient you'll be. I'll talk more about this, but if you've got human readable protocols or unnecessary repetition, then they need to go. You need to have good visibility of the problem. So you should have the ability to remotely manage your satellite terminal or access your satellite network, be able to analyze the data usage at an individual host and packet level. You need to know how to look at a packet capture file and spot the wasteful traffic. And then you need to see if you can control it. Maybe there's a load of data being generated by a host on your remote network that isn't required. It might be difficult to turn it off, but a good firewall running on your satellite terminal or in your network, which could be deployed and managed remotely, should be able to filter out any unwanted traffic. Maybe there's some configuration you can do to reduce the volume. Do you really need to send the same reading every 10 seconds? Or would once a minute be okay? Could you just send the data when it changes? Getting much more sophisticated, can you rethink your application to make use of edge computing? Here we're trying to make decisions on the remote device rather than transferring all the raw data to a server. An extreme example of this is video surveillance. We could deploy machine learning models to the edge So you don't need to stream the video all the time. Instead, we just watch the video and have the device transmit events when the camera sees a person or a vehicle. UDP is often hailed as a more data efficient alternative to TCP, and that is true. But I think in the context of relatively expensive and therefore presumably valuable information, UDP is unlikely to be a good solution. UDP packets have no guarantee of delivery, so they're a good fit for things like video streaming, where some loss or reordering just results in the picture becoming slightly worse. But if you're going to go to the trouble of redesigning your application to use UDP, then that effort is probably better spent moving away from IP entirely. Or if you're not doing it already, then you might consider using MQTT as your application layer protocol. MQTT is purpose designed for IoT, and it's much more data efficient than more commonly used protocols like HTTP. Just switching from HTTP to MQTT could massively reduce your data volume. MQTT uses a publish subscribe pattern, which can really simplify the topology of your network. It's no longer necessary to address a particular remote device or server, so it solves all the problems associated with dynamic or changing IP addresses. It's an incredibly lightweight protocol, especially when compared to HTTP, and it has some cool features like quality of service attributes, so you can mark some of your data as more important than others and demand higher reliability for that data. Some say that a drawback of MQTT is that it has no inbuilt encryption or security features. This is rarely a problem in a satellite context, as it's very likely that you'll consider the underlying network to be secure or private.
So there's some considerations for TCP/IP. Now thinking about messaging as a sort of segue into how we go about implementing messaging and how you might want to do the same thing. So, I mean, what's good about it, for many of the reasons that I touched on at the beginning, it should be one of the most cost-effective ways of getting your data over a satellite for IoT if your application can handle it, because you'll only send what you need. You'll only send it when you need it. So you can send less data, you can send it at the right time, and you can send it in an efficient way, and those are all super useful. Also with IoT, often power is a consideration. We recently worked on a project in very northern latitudes where the whole thing had to power itself off a solar panel and a small battery for 8 months of the year. So low power was design criteria number one, and physics being physics, if you want a terminal to be powered up and sending massive amounts of bandwidth all the time, you're going to need lots of electrical power. So messaging again helps you with power management, but it's really typically most well suited to well-defined and small amounts of data sent sporadically or periodically rather than continuously. On the cons, and I don't so much position these as negatives, more as design considerations while you're thinking about this, almost invariably there is some engineering effort required to deploy messaging for IoT. It could be a little or it could be a lot, but particularly when a lot of applications started out with, I'll just plug in my TCP/IP connection, you're probably going to have to do some work. The data volumes kind of may limit you. It's not suited to interactive two-way applications, and it does mean that, if we take drones as an example, it's very well suited to telematics for drones. If you use messaging, is it well suited to beyond visual line of sight control? Probably not. Would it be well suited to getting pictures off the drone? Possibly, if they were images. Probably not if they were video. So all of this stuff has to be considered. And then probably really the big one is that pretty much all the messaging technologies, whether you're talking about SMS or Inmarsat Data Pro or Iridium SPD or any others, invariably you're dealing with something proprietary, and that means you'll have to do some customization to deal with the proprietary aspect of the solution. So yeah, let's let Rick dive into the details.
So yeah, when we're thinking about implementing messaging, you've got to think about both ends of the application and the content of the messages between them. On the remote device, you'll have to integrate with something to send and receive your messages. And this could either be a high-level API, it could be an HTTP endpoint running on an IP network in your remote network, or you might choose to integrate with the satellite modem at a much lower level where you're speaking a proprietary protocol over a serial port, something like that. Now that we're in a messaging world, we pay for every byte of our message and nothing else. And that means that if we can halve the size of our payload or the useful information we want, then we pay half. as I said earlier, we often see messages that a human can easily read, and this is always a clue that there's a lot more efficiency to be gained. Computers don't speak English. In this example down the bottom here, we're using 153 bytes of information to represent a position report from a tracking device. And we can easily reduce that to about 8 bytes, which is what's shown on the right there, without losing any important information there. It's just that a human can't understand it. Computer's fine. There's some other things to consider in this example. Do you need the position to be accurate to sub-millimeters? Do you need the date, or could that be assumed server side? Do you need to send the tracker's ID, or do you get that for free from the metadata you receive with the message from the network? And then on the server or the cloud side of the application, you need to be able to interact with these messages. And happily, many messaging platforms, because they're slightly more modern, platforms like Cloudloop, they're cloud friendly, clues in the name. They already have native support for public clouds like AWS and Azure, so they support queues and their storage mechanisms like S3. So this development on the server side is usually not an obstacle. It's normally using paradigms and patterns that programmers actually want to adopt. The obvious challenge to adoption of messaging services is that they are proprietary, and so they might create vendor lock-in. That said, there aren't so many vendors, and probably even fewer that are perfectly suited to your application, so that may or may not be a problem. Messaging services are connectionless, so while you can get positive confirmation that the message was successfully sent, you don't get a real-time response from your server. This is usually fine for IoT, where there isn't much conversational traffic, and the latency is a little higher. We're probably talking a few seconds to get the message end to end. By comparison, a TCP connection, which might take a few seconds to establish, once it is up, could have a round trip time of around half a second. So they're just a few differences really, and things to think about when implementing messaging. On the screen here are a few of the most popular messaging services that are in the wild today. Both Iridium's short burst data, or SPD service, and Inmarsat's IDP, or Inmarsat Data Pro service. They've been around for about 10 years. They're pretty similar in throughput speed, although IDP does allow larger messages. Iridium's SPD is typically a little more expensive because it's a more resilient service. Iridium have more satellites that are moving all the time. They have smaller modules and antennas, and the service is truly global. IMT, or Iridium Messaging Transport, is Iridium's new service, and we're only just starting to see hardware roll out for this. And Inmarsat have a similar service coming along soon called OGX. It's much more suitable for sending a few kilobytes of data, so you could send pictures or just higher volumes. And this service is likely to drive down the price per byte for messaging services that do require those slightly larger payloads. Finally, I wanted to show you how some of the ideas we talked about can be combined, and talk about how a ground control service that enables you to adopt message-based satellite transport without you having to write any proprietary code. We call this somewhat unoriginally our IoT gateway. We basically take the MQTT picture that you saw earlier, and we break the MQTT broker in half. So we run an MQTT broker on the satellite terminal, which is actually our ROC remote terminal. The sensors in the remote network can interact with that broker exactly as if it were the broker it used to talk to in the cloud. So they can't tell the difference. We also run an MQTT broker in Cloudloop, which is an AWS hosted service. The server side of your application can interact with this broker exactly as it did before, so it can't tell the difference. And then we join up those two brokers using messages carried over IMT. If you happen to have an application that already uses MQTT, this solution could drop in with no change required to either the remote or the cloud side. They'll magically just work as if they would over a cellular network. The latency will be higher, as we said. There are some caveats. We don't implement the full feature set of MQTT. We're just trying to use that link as efficiently as possible. But if you are able to do this, then you'll be using the most data and cost efficient way of using satellite comms with little or no effort and with very predictable costs. That's all from me. Back to Asta.
All right, so just to bring it all together at the end then, right there at the top, I've got this first question, which is the extent to which you have the ability to innovate and change your existing application that is most likely to have been based on IP when it was first sort of invented, conceived. Because if you can't, then almost by definition, you are down an IP-based communications route. And the topics that Rick talked about earlier about how if you're going to use IP, you can make sure you're using it well and using it efficiently apply. Think about, can you send less data? Think about turning ports off on firewalls and so on, so that you really limit the satellite link, which tends to be more expensive than cellular link, and it tends to be slower than a cellular link. So you can do the best you can whilst using a very reliable but slower, more expensive link. If you're ready to change, able to change, and we know from experience some can, some just can't, for a lot of different reasons, then we would always say as a starting point, think about what you can do to optimize your data. Are you sending data you don't need to? Could you encode your data or compress your data in a more efficient way? So taking Rick's example, 53 bytes becomes 8 bytes. There's often a lot of discussion in satellite around can we reduce the cost of the airtime by 10% or 15%? If you reduce the amount of data you're sending by 80%, then you're definitely off to a good start. And once you've done that, you fundamentally have two branches. You have the more, I hesitate to call it standards-based, but the more standards-based route. If you can easily adapt to MQTT, then you only kind of have to do that once and you're into the MQTT world. The other world is probably where we spend the most of our time, what I've labeled here as a proprietary solution. Invariably, there's more engineering effort to go down that path, but there's a high likelihood of a range of potential benefits if you go that route. That route opens up the potential to say things like, I'm prioritizing low power as my requirement. I'm happy to live with messaging, but I don't mind talking to a satellite modem using a serial protocol, for example. So that way, once you go down the proprietary route, you're adapting something probably at a relatively low level. Even down that proprietary route, you'll still have a TCP/IP choice if you want one. And at that stage, you'll have done all the optimization and sort of reconfiguration you can, and quite possibly change the way your application works to suit that environment. And then bottom right, that's probably home territory for us. The lowest level of integration could be you've actually got an application talking a good old-fashioned serial protocol down an RS-232 link to a satellite modem. So, I mean, most of the problems, I guess I would summarize by saying pretty much any problem can be solved if the application itself is high enough value and the desire to retrieve the data from a far-flung place is high enough, or the importance of it, the criticality of it is such that you want to incorporate satellite IoT into your solution. There's always a way. And here we've tried to lay out for you everything from what I would call essentially a sort of a plug-and-play TCP/IP-based solution at the top left on this page, all the way down to kind of re-engineer the terminal, re-engineer the application, and really get kind of down with the guts of satellite IoT at the lowest level. So there we go. That's all from us. That was our second of this sequence of 6 webinars. I hope you found it useful. You know where we are if you want to chat to us. And meanwhile, I'll say thanks for watching, and I'll hand you back to David.
This brings our webinar to a close. I'd like to thank Alistair and Rick for their insightful presentation and Ground Control for sponsoring today's event. You can view more webinars at iotcentral.io. Thank you for watching.